This is a solution to rigid body kinetics number 16. I'm just going to do the B part. You've done things like the A part play. But you have a pulley. Let me make this, draw it a little bigger. And you have a mass hanging from a cable over one side of the pulley. Say this mass is 50 kilograms. And then you have a 600 Newton force on the other side. And the question is, if the pulley has a radius of 0.1 meters and a mass of 3 kilograms, what's the acceleration of that block? Well, if the pulley is frictionless, and well, it's still frictionless, but if it's massless and you're not worried about the dimensions and stuff, you're going to get a relatively high acceleration of this. We're going to see that when you deal with a real pulley where that disc has a radius and has a mass, the acceleration is going to go down maybe a little bit, maybe a lot, depending on how big the pulley is and how massive it is. Usually the mass is so small compared to the other forces you're dealing with that you can get a pretty good approximation by thinking that it's massless, but this is how you would include the mass if you want to. Okay, so let's see here. So I'm going to start by doing a particle kinetics problem with the 50 kilogram mass, and we're going to get some stuff that we can set aside for later. So free body diagram of the 50 kilogram mass. You have a weight force down of 490.5. And you have a cable force up. And the thing that changes, the first thing that we see that changes if you're dealing with mass of a pulley is that the cable tension on the mass side is not the same as the force applied to the cable on the other side of the pulley. So we just have to call this T. Okay, we don't know that that's 600 newtons. And now we'll go to Newton's second law. You get 0T plus 0, negative 490.5 is equal to 50 times 0A. The x equation doesn't tell us anything. The y equation says T minus 50A is equal to 490.5. You can't solve it because you have two unknowns, but we'll come back to it. And now, if we weren't dealing with a pulley with mass, we would have been able to solve this problem right from there. We'd be done with this problem. But because that T would be 600, and you can just immediately calculate A. But so now we're going to have to do the rigid body problem for the pulley. And so I'm going to go through the steps in order of how to do a rigid body problem. First step is, does this pulley have a fixed point? It does. But the fixed point is the center of mass, so the about point is the center of mass anyways. Now it's pretty easy to calculate the mass moment of inertia. We don't have to use parallel axis theorem. So the mass moment of inertia about the center of mass is 1/2 times the mass times the radius squared. So that is 0.015 kilogram meter squared. And now we'll do a free body diagram of the pulley. There's a force vector there from the pin. I'll call that R. There's a weight force of the pulley. That's 3 times 9.81. Since these two things are both happening at the about point, neither of those is going to come into the rotational, the moment equation. And then we have here a cable force, T. And over here we have a cable force of 600. So row vector, force vector, moment vector. So first, let's think about that 600 Newton force. The row vector, we don't know what that is because we don't know what the angle is to where it leaves the body. We don't know what the, we know the magnitude of the force, but not the unit vector, the direction it's acting. So that seems like problems. We could do it in terms of sines and cosines. It turns out that since we have a fixed point here, we're not going to use Newton's second law. And so as long as we can calculate the moment produced by this 600 Newton force, then we're good. We're only going to use the moment equation. And that moment is just going to be, since that force is tangent to the pulley wherever it leaves, it's just going to be a clockwise moment with a magnitude of 600 times the radius of 0.1. So it's just going to be negative 60. And since we're not going to use Newton's second law, we're okay with that. The reaction force, there's no row vector. Again, we're only going to use the moment equation, and so all we really care about is that that produces no moment. Same with the weight force. The row vector is 0. So whatever this weight force is, it's going to come out to produce 0 moment. And then the last thing we have to deal with is that force T. The row vector is positive 0.10. The force vector is 0, negative T. And so the moment is negative 0.1 T. And that makes me realize that, so when I did the 600, that would produce a counterclockwise moment. So this one should have been positive. Those two are opposite each other. Okay, no Newton's second law. And so we'll go straight to rotational Newton's second law, and we're only using the Z component. And so it says 60 minus 0.1 T is equal to the mass moment of inertia times alpha. And so we have a second equation now that says, I'll write it as 0.1 T plus 0.015 alpha is equal to 60. That's our second equation. But we also added a new variable, right? So now we have a system of these two start equations, but we have 3 variables. But the key thing now is we can relate the acceleration A to alpha. We know that the acceleration of, the acceleration of that block, that's the A in the first Newton's second law, is the same as the vertical component of the acceleration of that point on the pulley. And so we can, let me name that point on the pulley. So I'll call that P. Okay, so the acceleration of P is equal to 0, 0, alpha crossed with the r vector, 0.1, 0, 0, plus omega cross r. But this one's going to go away. That's the centripetal part of the acceleration. We only care about, all we care about is the y component. Okay, that's what we want to relate to the acceleration of that mass. This one's horizontal, so we don't care about that. Okay, so the y component of that acceleration is 0, positive 0.1 alpha 0. So our third start equation just says A is equal to 0.1 alpha, so A minus 0.1 alpha is equal to 0. And now we can solve this, let's see. So we're going to solve 3 equations for 3 variables. Okay, so let's say alpha, so we know that alpha is equal to 10a. So I'm going to plug that into the second equation, and we get 0.1t plus 0.15a is equal to 60. And I'm going to solve that with the start equation. So t minus 5a is equal to 490.5. I guess I'll multiply this one by negative 10. That one gives you negative t minus 1.5a is equal to negative 600. Now I can just add those two together and it'll eliminate the t, and we get 6.5a is equal to so 6.5a is equal to 109.5. And so a is equal to 16.85. Okay, how does that compare to what we would have gotten for part A? Well, for part A, all we would have just been done as a particle problem, we would have known that T was equal to 600. And so we would have had 109.5 divided by 5, we would have gotten 21.9. So the mass and the size of that pulley decreased the acceleration of the mass from 21.9 meters per second squared to the answer that we got, 16.85 meters per second squared. And that's the solution to rigid body kinetics number 16.